Okay, welcome everyone to the radio network planning lecture for today. I'll be covering a number of different topics in relation to network planning of the mobile radio access network. And you'll see here from the course outline that we're getting close to the end of the semester. We have really a tutorial week this week, so we've sort of advanced the radio planning lecture. So next week might be a little different. But we do have two remaining lectures left, which is the HSDPA and the 3GPP long-term evolution lecture as well, which will finish off the rest of the course. And then your last week will be a revision week. So what are we going to cover today? There'll be 6 key areas, the first of which will be a generic sort of overview of radio network planning. And then we'll look at a very important aspect, which is the dimensioning of the actual network. So what I mean by dimensioning here is effectively in terms of capacity and coverage. So how many subscribers can we support on this mobile network, and which geographic regions can be supported. The radio link budget is a very important part of that, because that defines effectively the physics, if you like, of the radio network and what the capacity should look like and coverage. And that leads us on to the next part, which is optimization, which is again an important area of the radio network as well. So that is, we start off by making some predictions based on modeling tools around what the coverage and capacity of the network will look like. And then once the network is launched and real traffic is on the network, we need to use real data to optimize the network. So that's where the optimization part comes in. So the feedback loop is from real data. And then we'll have a look at the planning between GSM systems and wideband CDMA systems and how they coexist. And then I'll just show you a few slides on radio network planning tools, or RNP, and some of the pictures and how they look. So we're on about, I'm looking at finishing up at about 8:15, so a little bit of a shorter lecture today. So we can still have a break if you like, but if we can keep it very short would be good. I'd prefer to finish a bit earlier, or if you like, we can run straight through. So well, let's see how we go in about 45 minutes. If you're still awake, then we'll continue. Okay, moving on to slide number 5. So when we look at the overview of radio network planning, really what it comes down to is today's scenario and a scenario for tomorrow. So what I mean is that we need to build a network based on supporting today's requirements of subscriber traffic. So the amount of minutes that you will talk per month, for example, times the total number of subscribers in the network. That governs the capacity if we're just looking at voice. Also, you now have a data requirement, which is a certain number of kilobits per second or kilobytes in a total month, for example, which is now turning into gigabytes, actually. When we first started giving this lecture, no one was downloading anything more than probably 10 megabytes per month, if that. Now we're looking at people with over a gigabyte. So you can see the rapid growth. So also, we need to take into account then the future scenario as well. So if we build a network today, or at least if we plan for a network today, it takes maybe 6 months to build. So in 6 months' time, do we run out of capacity? We don't want to be in that sort of situation. Ideally, we want to plan ahead as well. But if we plan too far ahead and we build a network that is suitable for traffic in 3 years' time, then we've spent all our money in terms of being an operator. So we've got a balance to make here between the economics as well as supporting the actual use cases that we have. So the objectives in brief really are those 4 points, which are very important to remember, are capacity, as I've described, coverage, which regions are we going to cover. So some of the choices that we can make as operators, for example, rolling out a new mobile network is, do we do it nationally? Do we start with metro cities only? And do we start with metro plus rural, for example? Or do we focus on key markets or key areas where our business is quite strong, for example? Some technology choices might imply that we only roll out hotspots, meaning that we go for areas like airports, highways, those sorts of places. to start off with, hotels. We also then need to manage the quality of the network as well. The important point about the radio network here is that it's very different to the fixed network. When you pick up a telephone at home and you're using the PSTN to make a voice call, you can generally say that almost 100% of the time the voice quality is pretty much going to be the same all the time. It's a matter of whether you get on the network or not, but I don't think anyone's ever been blocked picking up their fixed phone to make a voice call, in today's age at least. But for the radio network, it's a totally different story. The quality aspect depends on your signal strength, how far you are from the base station, whether you're being blocked by buildings or trees and all those sorts of things which the fixed network doesn't have to worry about. So the quality aspect then comes into the play as well. And the most important part of the quality part here is the terminal as well, or the handset or the handphone. Not all phones behave the same. Some phones are better designed and require less power from the base station to operate at the same level. So those factors need to be taken into consideration, and we'll discuss that a bit later. And the fourth and final point then is in regards to costs. As I described in the sort of extreme scenario, you don't want to build a network from day one covering your 3-year plan already in one go. It's simply not affordable. So you need to balance the cost and the benefit of that. So really, that's really the 4 key points in that slide, and that's all I'd like you to remember, and think about the examples that I've given you, because that'll help you remember the key areas here. So if we move on to the next slide, let's get straight into a process here. This is just an example. I think it's taken out of one of your texts. I think it's the Toskala book if you want to have a look at it in more detail. So we start off with, like any sort of process, we have an input and an output. So the input components here are our coverage requirements. So let's say, for example, we're UTS.com mobile operator. We're launching LTE in Australia. Given that it's a 100 megabit per second peak download data rate, for example, where would you think you would start rolling out a network with that kind of peak speeds, given that today we only have, say 14 megabits per second? CBDs? Okay, CBDs is a very good guess. Any reason for why CBDs? Bandwidth? Okay, so the answer there is the businesses and enterprises exist in the CBD. They tend to use more bandwidth, and they also have more money to pay for these types of services as well. So I think that's a very good answer, in that, for a high peak data rate type technology like that, you'd want to be rolling it out where the consumer was, or the businesses are, and who have the capacity to pay for it. The problem you also have then with CBDs is it's a high dense area as well, right? So you have a large number of people living in a small space, usually in buildings, also very high up in buildings as well. So you have to cover floors 20 and 30, for example. So you have that complication. So you have to maintain the radio quality, making sure that you get this coverage in the CBD to start off with in this scenario, and maintaining the capacity that we're after. And then this really comes down to all the radio propagation characteristics, which is the 4th point here, which is what I discussed in terms of building, terrain, clutter is what we call objects that actually block the radio signal, so trees and buildings and so on. So when we take these 4 inputs, we then actually put this into a planning tool. Usually it can actually be quite a crude tool, in that it could be a simple Excel tool at the very basic level. But most planning tools are actually quite complicated, and several companies have been making these tools for a very long time now. And these simulations run overnight or over several days in order to project whether the radio signal will be sufficient to run the capacity and coverage that we want to achieve. So then what we have here is, you see the dimensioning section here, and then as an output, in many ways, at the end of the day, we get a number of base stations covering a certain number of area. So that gives us our base station density. So how many base stations per square kilometer, for example. So in the early days, what we can afford to do is when the capacity is quite low, we can afford to roll out a much larger coverage area by using less number of base stations. Because if you think about it from a mobile operator point of view, you want to reach as many customers as possible in order to increase your business. So the idea is to generally maximize coverage in the beginning, and as consumers get onto the network, loading the network, you then want to improve the capacity. So your scenario changes over time. So that's something that has to be modeled as well. So when you figured out the number of base stations that need to support a certain area, you need to actually figure out where to put these base stations. Where is the most optimal location? Now, a planning tool ideally will probably uniformly spread them out in a very crude sense, but it has to take into account the buildings, the terrain. You can't put a base station in the middle of a lake, for example. So these planning tools are quite sophisticated, and they take in map data, very detailed map data, and the resolution is usually 20, 30 meters in resolution. So what the planning tool is able to do is then figure out where the most appropriate place for a site is based on the capacity and coverage that we want to achieve. Using also the input parameters of the radio quality and the propagation that we discussed, characteristics of the environment. So the output at the end of the day will become the number of base stations, where these base stations are located, and general high-level parameters in how the base station should be configured. What power level should be output, what should be assumed for the mobile phone, and so on. So together the whole system should really work. And this is what a radio frequency engineer will be doing on a daily basis, is this type of planning. So when we talk about cost, it's also quite important here too, because every base station has an associated cost. We also need to purchase the land around the base station, or potentially lease the land around the base station. So if you take an example like Telstra, who has the Next G network in Australia, they have 6,000 base stations around the country. Each of those base stations requires a plot of land. It also needs transmission to go from the base station back to the network. So all of those links cost a lot of money. So you don't want to be just randomly allocating sites and building up too much capacity and coverage too early, because that can actually be very bad for your business case. So moving on, some of the radio network planning methods. I discussed a little bit of this in the introduction, but the most important first step, if you like, or the first step is the preparation and evaluation stage. So this preparation and evaluation is really about what coverage do we want to hit? Is it CBDs only? Do we want to extend that to the main metro centers of the capital cities of Australia, for example? So if we take Hutchison Telecom, which is the 3 network, so when they rolled out their network, they chose, I mean, they're a startup company, right, essentially in Australia. They had the Orange network running a CDMA technology, so there was some cash coming into the door from that business. But the 3G business was completely brand new. So where would you want to pick your first sites? So they chose to build out a network, a 3G network in Sydney and Melbourne to start off with, which makes sense. I mean, it's got the bulk of the population. So they started in Sydney and Melbourne, and then after that they rolled out Brisbane, South Australia, Darwin, and WA. But they've kept it to very much the capital cities, because that's also what their license holds as well. But if you look at 3 Mobile, for example, they don't really market to the farmer, the construction worker, the rural consumer that much. They're more of a player towards the city dweller, the younger population. So it made sense to focus on the capital cities. So you can see here that the engineering part of it takes in inputs not only from a technical standpoint, but also the business case coming from the company as well. What is our marketing plan? How do we expect to, seek revenue from this venture, and then therefore make it profitable? So once all of those input parameters are sort of gathered and a strategy or rollout plan is in place, we start to do the initial planning, which is what we looked at in the previous slide, going through that process of input, modeling, and then output, and we iterate through that several times. It's not you do it once and you get an answer. So there's a lot of tweaking and adjustments that need to be made. And then once we are a little bit more certain, we get into the detailed planning phase, And in that situation, we start to look at the antenna types, exactly the configurations of the actual equipment, how the equipment will be configured, the transmission, all of those little details. We also look at the code planning and all of those aspects as well. Once we've finished with the detailed planning, there's two parts to the next phase, which is optimization. The initial optimization is you need to start the network with some level of configuration. So based on the planning tool and some experience from engineering and the RF engineers themselves, we can start off a network with an initial configuration. So that's called the initial optimization piece. Once the network is launched and we've got traffic on the network, then we can start to see how the network is performing and then tweak the models and then update. So then we can do further optimization. So optimization is usually carried out by drive tests where it could be in a van with test equipment and people are driving around and looking at the signals and seeing how fast the network is running. Some optimization tools are quite clever. They work on themselves. They're automatic tools. You can leave them in buses and taxis and so on, and after a week you can pull them out of the cab and collect the data and then analyze them later. So there's a number of different methods around how that can be achieved. And then the final step then is that you will ideally like to verify what you see in reality with the model, which is the last step here, which is the verification phase. If your view of the real world is quite different from what's actually happening, then you have a problem with your modeling tool and you need to tweak it as best you can. You'll never ever get a perfect model, but you want to get something that is very close and reliable, that gives you a very good start. So in the next section, we're moving into dimensioning. And in dimensioning, I'd like to spend a couple of slides going through this just to explain how the process works. We talked about 4 parameters earlier in the beginning slide of coverage, capacity, quality of service, and cost. So in this one, this slide will be looking at the first 3 of coverage, capacity, and quality of service. So if we look at coverage, for example, we've got the regions we want to cover, and then we have, as per that, the propagation characteristics. Is it hilly, lakes, and so on? For radio frequency planning, buildings obviously pose a very big problem because radio signals bounce off walls. They also pose another problem in terms of in-building coverage, where radio signals find it very difficult to get through solid matter, for example. So you don't want to build too much or have too much site density in the CBD areas, because that increases your costs again because of the number of sites. But sometimes you may have to in order to cover the in-building from outside. Thanks for closing the door. The other part of capacity is the spectrum availability as well. Now, you as an operator might have 5 megahertz or 10 megahertz, for example, of spectrum. If you only have 5 megahertz of 3G spectrum, for example, you have to be very careful in terms of how you plan. And then you've got to take into account your subscriber growth forecast. How many subscribers are you adding per month? Does anyone remember the figure I gave or asked for China and India in the very beginning? How many subscribers are added in each of those countries each month? Sorry? I'll give you a clue. How many million subscribers are added per month? 10, was it? Yeah. Somebody said 10, yeah. You get the chocolate fish prize. So you've done well. So it's 10 million subscribers are added in India and China each month. So you've got a growth forecast to take into account here. And there's the traffic density information. So what do you think that the traffic density information means? I gave you a bit of a clue at the beginning of the lecture. It's really about the subscriber's behavior. How many voice calls am I making per hour, for example? How long are those voice calls? And, for example, data calls as well. How much am I downloading? There's a couple of key characteristics that are used. One is called the busy hour call attempt, which is the BHCA. And that's used during the busy hour. Actually, I should probably mention the busy hour varies from network to network and country to country, but typically between 5 and 6 o'clock is a peak period when everyone's finishing work and going home. They're all talking to their friends and loved ones. So you'll find when you look at the traffic in the network, it actually peaks during that period. But during the day, it tends to be a lot lower than that, right? And then maybe in the evening around 8, 9 o'clock, you'll notice another peak, which is typically around the voice calling, but more so around data downloading. People are surfing the web and doing things on their mobile at that time. And also you find a bit of a peak in the morning and lunchtime. It's quite typical. So if you're trying to plan a radio network, you need to build a network to cater for these traffic peaks, right? But you can't build a nationwide network covering 20 million people assuming that they'll all be peaking at the same time. You see, the economics of the problem here is that you'll build a very, very big network that will be extremely expensive. So as a network planner and designer, you've got to make the call and the decision around exactly how much traffic can I actually support. And not all the traffic is in the same place either. It tends to be in CBDs or in hotspot areas and so on. So you need to have very good data or traffic density information of your network and what are your subscribers doing. If you get it wrong, you can actually end up building a very expensive network. The quality of service then is around blocking. There's nothing worse than trying to make a mobile phone call and you can't get through. In the early days of GSM networks, that used to happen quite a lot, but you don't see that happening very much in developed markets. It tends to be a very big problem in developing markets and emerging markets around the world today, because they have the limitation of spectrum usually. So in only 3 or 4 megahertz, for example, in many Indian operators are able to squeeze a huge number of subscribers in there, which we don't see in countries like Australia. So they employ very clever RF techniques to make that happen. And at the end of the day, the last piece, which is becoming more and more important, is the end user throughput. Now that more and more users are using mobile broadband, it's becoming quite important to be very accurate with their data planning. I don't know if anyone has seen maybe a week ago something quite current. Optus, they removed their Fusion plans off their mobile broadband. I see a couple of nods here. I don't know if anyone had access to that plan, but they copped a lot of flack in the press for that because it became obvious that they hadn't built their network with a sufficient capacity and coverage to support that type of aggressive plan. So they looked it was quite embarrassing, I think, for Optus if you look at it from a broader context. And that's a direct consequence of not having done what we have talked about. Now, part of their problem in their defense was that they were somewhat, I suspect, CapEx constrained, so they didn't have enough CapEx to roll out a strong enough network to handle those types of services. And also what we're seeing in the marketplace today is the take-up of data is very, very high, and it's very difficult to predict what consumers will do. So if we look at the next slide here, slide 12, this is an old example that I'd like to just take you through very quickly. There is a very important concept here, and I keep talking about it over and over again today. It's this trade-off between capacity and coverage. So a base station has a certain amount of power, usually 20 watts in the early days, but now a lot of them are becoming 40 watts. All that means for you really at the end of the day is that the base station can either allocate, if you like, that power to capacity or coverage. So coverage, it's a bit more intuitively easier to understand. If the base station is powered very highly, then the radio waves will actually propagate much further. Therefore, you get bigger coverage. It's very similar to a stereo system where your speakers are, say, 200 watts. You crank up your amp, someone can hear you down the street, whereas if you turn the amplifier down, they can't hear it at all, right? So that's the coverage aspect. For the capacity component, how does power of the base station impact capacity? In order to run each service, whether it's voice, packet data, say at 64 kilobits or 384 kilobits per second, each of those services will require a different level of power from the base station in order to operate properly. So the higher data rate services will actually take more power, and the lower data rate services will take less. So voice services typically run at 12.2 kilobits per second. So you can generally fit a lot of voice services into a mobile cell. But if you have a lot of people using high data rate packet services as well as making a lot of phone calls, then the base station tends to be very loaded. So think of each of the discrete services like the 64, the 128, and the 384, all requiring different levels of power. So usually what tends to happen is that you wouldn't want to have 384 kilobits, in this particular example, provided throughout the entire cell. Because if you're trying to provide high coverage and high capacity, you'll be taking up a significant amount of the base station's power, right? So the further you are from the base station, you need to have coverage to pick up the signal, and then you need significantly more power as well in order to have sufficient signal for the high data rate as well. So it gets quite expensive. So what that means in effect is that the high data rate services tend to be only supported very close to the base station, and the lower data rate services tend to be supported quite easily further out from the base station. So what you tend to have in a mobile network in reality is what we call these service areas. So I've drawn them here in three ovals. The 384 kilobits per second service area is pretty much guaranteed when you're, let's say for example, within half a kilometer of the base station, as an example. But in order to if you're heading towards the edge of the base station or the edge of the coverage area, you could probably only get 64 kilobits per second. So what will actually happen is as you're moving further from the base station, you're going from 384 to 128 to 64. Your actual speed will drop slowly. So this is a release 99 3GPP service, for example, the 384. Whereas nowadays we have something called HSDPA, which is a lot more efficient in delivering higher speeds. But HSDPA suffers from the same situation as well, which is the further you are from the base station, the lower the data rate that you'll actually achieve. It's not a big problem, but the only thing you need to understand is that when you come around to planning the network and guaranteeing certain speeds to the consumer, that you take these factors into account. So I guess generally speaking, people outside of the industry would feel that when companies brand their service as you can get 7.2 megabits per second peak download, for example, naturally you will think you'll get it everywhere in the network. But given a lot of the factors that I talked about, where you are in the network, where you are in the cell, more importantly, are you in a building, are you being blocked by trees, how far you are from the base station, more importantly, will all impact what that speed to your mobile phone or your achieved throughput will actually be. That's why you see people talking about peak speeds. So in ideal conditions, you will get these data rates. So how does it look like as an example? So slide 13 shows us 3 base stations. And we have site 1, 2, and 3. The radio network planner here in this particular case has provided speeds of packet 64 throughout the entire network, which are in yellow. Together with that is CS voice or circuit switch voice, which is our standard speech service. But as we move inwards towards the core part of the network where the 3 base stations are, we can only support 128 in the downlink, 64 in the uplink, and then even more closer to the base stations, we see some spotty coverage of 384. So in reality, the 3G coverage, although it might be the big area in black, so yes, we are providing you 3G coverage, but with different degrees of quality throughout that network. Okay. So in this particular example, we've just defined a packet data zone as the red polygon that is drawn around site 1, 2, and 3. So if we take a real example, this is a real map from an actual city for an operator, and the black polygons were defined as the total area of 3G coverage, and so anyone within that black polygon will receive a voice service and 64 kilobits of data. But if they were to receive or wanting to pick up high data rate services, they'd really need to be within the red areas. Generally speaking, operators don't publish this type of detail, although they're starting to now, where they give people a bit of an idea of where the data speeds are. But internally within a mobile network operator, you'll define quite clearly where you would want to have the high data speeds. So you can see from the map, the darker colors, they're obviously high density, so that's where people are living, and that's where the CBD and the business districts are. And the top right-hand corner where it says the packet data zone, that's actually an airport, so that's why that area is being covered, which is different to the bulk of the red areas below. So that just gives you a feel, and the map output or the map data will actually help you get to this point. Okay, we can move on to the radio link budget piece now. Moving on to slide 16. So in much the same way that we looked at in the previous slides, on slide number 6, which was the RNP process, where we had the inputs and the outputs. Now we're specifically looking at the process for the link budget. So the link budget is defined as the radio characteristics, if you like, between the base station and the mobile phone. So that's what we're dimensioning for. So there's many dimensioning points throughout the network. So the first point would be to go from the phone to the base station. That's our radio link budget. Then from our base station to the top end of the radio network, which will incorporate transmission. And then we have to go to the core network, and then over to an ISP, and then the open internet. So there's lots of different steps involved. But right now we're only focusing on the radio link budget. So what we have is the link budget calculation. So that's the first step, really. And one of those calculations is what's called the path loss. So if we were to power up the base station at, say, 15 watts out of the 20 watts, how far would that signal go? It has a natural attenuation based on laws of physics, which I'm sure some of you have covered already, or it might be part of a lab. And then from there, you can actually calculate what the typical cell radius will be based on the path loss. That's a path loss calculation. So that's the first calculation that's actually made. And then from there, you can actually work out the maximum cell range. Now that cell range will be impacted by the clutter information. So the buildings, the trees, the hills, the lakes, all of those sorts of things. So then from there, we can actually work out what capacity and coverage, or what coverage we have, and what capacity we could potentially support. So then we make an estimation of the traffic, and from there we input, or we actually get as an output as well, the number of sites, the total traffic, and the subscriber density. And then the output that gets delivered is, as we discussed, the number of base stations, or node Bs in the 3G case. So some of the inputs to each of these steps are, so if we take the top right here, the equipment specific parts, or the inputs for the link budget calculation, is, for example, the UE power class. So all that really means is what type of terminal or user equipment do we have? What's the maximum output power of that terminal? What is the sensitivity of that terminal as well? Some mobile phones, as I mentioned, are more sensitive, which means they require less power than in order to operate. So the better mobile phones will actually work quite well with HSDPA, whereas some won't. Now, you as a consumer going to buy a phone, you wouldn't ever check the UE sensitivity, and it probably would never ever be published. It might be at the back of the manual, for example, but it's not really relevant to you. I mean, there's a lot of other factors that go into whether a terminal will be quite useful or not, or well designed. In the early days of 3G, around 2001, 2002, many manufacturers tried to build 3G phones, but some of them were quite bad. And some manufacturers had phones that, I think the number was around 5 or 10 dB poorer sensitivity than the best phones, which is significant. So we used to call those phones quite deaf, because they needed a lot of power in order to operate. So you'd use 3 or 4 of those phones in the mobile network or in a radio cell, and you'll find that it will actually cause congestion in the mobile tower, and then sometimes it would shut down the tower in the very early days. Now things have moved on quite well. I mean, it's 7 years on. Most manufacturers are actually making good quality phones. But as technology evolves and the phone gets more complicated, we have a lot more features like long-term evolution and HSPA evolution in order to build into the phone. The challenge is still there for a terminal manufacturer. In terms of the cell range calculation, the base station is one very important component. I've talked about the propagation environment. The other one, of course, is the antenna. The antennas themselves have a gain in them as well. So there's a power amplifier in the base station that sends the signal to the antenna. The antenna has a further gain, and then the signal is then shot out of the antenna, if you like, and then there's attenuation effects start to kick in. So the type of antenna, the gain of the antenna is very important, and also the height of the antenna is extremely important. So naturally, the higher the antenna, the further the propagation as well. So all of these things need to be taken into account. So if you look at the antenna height as an example, then if your radio tool came out and said you need to have an antenna that is 40 meters high in George Street, what would you say? It's not really practical, is it? You can't really have a 40-meter antenna in George Street, although you could have a 40-meter antenna out in Dubbo, and that would probably cover 5 or 10 kilometers. So a planning tool is not generally going to do something like that, because what you can do is you can mount the base station antenna on the side of a building, and you could get your 40 meters that way, but you wouldn't need a monopole, for example, to achieve that height. The higher the height as well, of course, the more expensive it is to construct that particular site. So although you've got the benefits of the height, you've got the cost aspect as well. So you've got this constant battle between the economics as well as the ideal radio scenario. Some other service characteristics then as inputs that are quite important is the peak traffic. Now we discussed this scenario of the busy hour and the peak traffic as well. So if you build your network to only support the average usage of the network, and if you assume that all subscribers are uniform, then that's a fairly simple model. It generally works, but where it will fail is in areas like the CBD or in hotspot areas or in areas where there's a high concentration of subscribers, like in airports and hotels and so on. So what will happen is your base station will be able to support the assumption of average traffic with a uniform distribution of subscribers. But when that peak occurs, obviously the base station can't deliver, so it goes into congestion. What you and I see as a consumer is a very slow packet data rate, and maybe even a blocked voice call as well in the worst scenario. So naturally we want to avoid that as well. So what we tend to do is we won't assume a uniform distribution of subscribers. We try to assume a very high level scatter, if you like. So you might say that people in CBD have a density that's 3 times greater than a suburban density as a rough metric, and rural might be half of the suburban, and that would be enough. You don't need to go too detailed. And then in terms of the traffic required in each of those areas, you could multiply by a similar ratio. So what that would mean is that the site density in those metro areas would be very high, and the site density then would decrease as you progressively move out to the edges of the network. And that sort of makes intuitive sense as well. So if you look at the radio link budget, there's a few interesting parameters in here, such as the interference margin, the fast fading margin, and soft handover gain. I won't go into too much detail around this because you'll be covering these link budgets if you haven't done so already in your labs. So a lot of the calculation pieces I'll skip over today. But the only main piece here that I'd like to highlight is if we move to slide number 20. Well, actually, let's go to slide 19, which is the radio link budget calculation. So in slide 19 here we have another aspect which we haven't mentioned, which is the speed of the subscriber as well. So the radio network plan, once you've figured out your coverage, your capacity, you understand your environment, you know the propagation losses because of that environment and the coverage and capacity requirements, you've got to then model the subscriber. So what you tend to have in is motion models where 3 or 4 models are typically taken into account. There's a 3 kilometer per hour model, so that's somebody walking, for example. There's also, for example, a 20 kilometer per hour model, which is someone being in a bus or a train, that sort of speed. And in very rare cases will you have what's given here, a high-speed model, which is the 120 kilometers an hour. So if you can imagine, you're trying to model mobile phone coverage in Tokyo on the bullet trains, for example, across their train lines, so that consumers can make voice calls as well as download high-speed data. You need to take into account the speed of the consumer or the subscriber, as that has an effect on the fast fading margin as well, which is essentially around the attenuation at the end of the day. So the next aspect here is the EBNO, or the energy per bit over the noise, commonly known as EBNO for short. So when I talked about the power of the base station relating directly to coverage, that was one dimension, and the second part was the capacity, right? And I said that each service required a certain amount of power in order to run. That service specification, or the power for that service, is specified by this EBNO value. So for a voice service, you might have a low EBNO value. For a 64 kilobit per second, the EBNO value will be 3 or 4 times higher. And for a 384 kilobits per second, it will be again 3 or 4 or even 5 times higher. That generally translates directly into watts, the amount of watts that are required in order to run the service. So that's what that component is. So it's a very important parameter in the planning. So mobile operators then can actually choose. I mean, there's no one right answer. There's a range of EBNOs that are required in order to provide a good speech service. So what some operators tend to do is they have a choice to make. They can either launch the network with low quality and market it as a 3G network throughout the country, or they could launch the network throughout the country and have high quality and provide good service. And the difference between those two scenarios are actually very, very large. And that's largely governed by factors such as the EBNO, the coverage and capacity and quality that we talked about. So what I'm trying to highlight here actually is that a lot of people refer to RF engineering and planning as black magic, because it effectively is magic in many ways. It's not as defined as fixed telephony services, where it's hardwired, you understand the connections, you have the copper cable, everything else is fairly discrete. With the radio component in there, you've got a high degree of variance here. We've already talked about probably 20 already parameters that are very important in governing the success of a mobile network rollout. So operators have a great degree of flexibility in choosing what they would like.
You talked about re-rolling out a network, and I'm just thinking for something like mobile broadband, where nothing like that's really available. Obviously 3G voice might be able to base on 2G, but I mean the theory is great, but where would an operator even begin to estimate things like what the uptake's going to be, how fast the user's going to be moving if something like mobile broadband isn't out there?
Okay.
Where would they even start? Do they just guess?
Yeah, that's a really good question. So just to repeat the question for the benefit of the recording. So mobile operators such as 3 and others in Australia, when launching their networks, it's understandable that they could model voice usage on 3G based on 2G. That's quite reasonable, and that's what most of them have done. But when it comes to packet data, how do they go about figuring out what it could possibly be? And seeing as we've discussed, the impacts are quite severe as well, because there's nothing worse than having consumers that are very frustrated by a very poor service, as well as a marketing department that can't win new subscribers because of that reason. And secondly, a chief technology officer who's responsible for the network rollout, who's got a network that doesn't work. He looks pretty silly in front of his CEO. So all of these things happened with all of the operators, at least from my experience, having seen it here in Australia. And how a lot of the operators launched it was, what you tend to have is, unfortunately, the marketing departments, where they set these plans and come up with these traffic models on a very high level, don't really have an idea of the impact on the engineering, which is fine, because that's not really their skill set. But the engineering side of it, the engineers within the organization, for example, need to help and educate and make the marketing department realize when they launch this 5 gigabyte plan for $49 a month, it's going to have this impact on the network. And that's a constant battle that happens between almost, I would say, most operators globally as well. So how did they, to answer your question more directly, how did, say, Hutch do it? I was involved at the time when Hutch was rolling out the network. So what they did was they started off by modeling their 3G voice on 2G voice, which is what you mentioned. The packet data was not so easy to do. And part of the problem also was that the vendors of the time, the manufacturers of the equipment as well, were also learning what their equipment could do. So what happened, luckily for the market, was the pricing plans that they employed were based on cents per kilobyte or dollars per kilobyte. So although the networks had a huge amount of capacity in the beginning, because it was so expensive to use, not many people used packet data. So it actually was a benefit for a lot of these operators who were able to slowly understand how the behavior of the consumer worked. So
was that a strategy though? Like, the price is high, so
I don't think it was a strategy. I think it was just the way things worked out, actually. They had no other choice. I think they understood that if they opened the floodgates and made it cheap, they probably wouldn't know what was going to happen. So they were sort of stuck in this sort of quagmire, if you like, to begin with. And part of the problem was that the 3G packet data services at the time were the 64, the 128, and the 384 that I mentioned. So those particular types of services, when you had a connection to a 384 service, you used that 384 connection all the time, even if you weren't downloading any data. So it was almost a connection-oriented packet service, which sounds quite crazy. So what that meant was it was very expensive to run these services, so operators were very reluctant to let the floodgates open. When HSPA came along, then things got really messed up in many ways, because the exact problem happened, which is they kept the pricing plans somewhat. Some operators decided to be a little bit more aggressive, and then the take-up just suddenly went off. And the main reason for that is that HSCPA tends to use a shared network or shared data channel. So you get the data rate based on your radio coverage and your requirements as best as the network can offer. So it's actually a lot more efficient because it's pooling the resources, right? So what happened, in much the same way, some operators took the step to offer bucket plans on data as they had done so on voice and SMS. And then almost every single operator around the world was having a 300% growth take-up rate. And it was just going absolutely through the roof. And all network operators, networking divisions within those, were struggling to meet up demand. Now, in the first instance, the problem came in the radio interface because the radio link budget wasn't designed to satisfy that level of data rate. But because there was hardly any subscribers on the network, or it was quite few, you could get away with it for the first maybe 3, 6, 12 months. But then they were able to open up the radio link budget, if you want to call it that, and allow more traffic. But the problem that the network had was the backhaul to transport the data from the base station to the core network was based on all the older traffic models. So what's happening today in the industry, and it's pretty much started as of, I would say, beginning of last year, network operators are now spending a huge amount of money upgrading their transmission backhaul from the base station to the back end of the network, because they can't transport the data fast enough. And that's very expensive because a lot of those links are all microwave links. They themselves are towers and wireless as well. So what you have is you have a wireless connection from the mobile phone to the base station, and then another sub-network which is built for the operator, only for the operator, which is based on microwave as well, with additional towers as well. And those links are usually only 2 megabits per second. And the usual capacity of those microwave links is usually 4 to 8 megabits per second. So if you're offering a service that's 7.2 or greater, it's not going to work, right? Well, you're not going to get the peak. So a lot of operators in Australia specifically, and it's mostly all the bottom three, which are Vodafone, Optus, and Hutch actually. And I mean bottom in terms of number of subscribers, not in terms of loser requirement. They're all doing fantastic things. The issue that they had was that they had very limited backhaul networks. But they still had launched 3G everywhere. They'd launched 3.6 megabits per second. but they couldn't deliver those peak speeds. So what's happening now in the marketplace is the incumbent telecom operators, which are the big ones like Telstra and Optus to some extent, are trying to wire up fiber everywhere to each base station. So if you can get fiber to a base station, I mean, you're talking 100 megabits easy, just to start with. So you suddenly go from 4 to 8 megabits per second to 100. So the dimensioning and the planning of the radio network that we're discussing here today has to match the rest of the network. As I mentioned, there's lots of other dimensioning points or bottlenecks along the way. So I think what's happening now in the marketplace is that the same confusion is still there. Operators aren't totally sure where the price points are for subscribers. So if I offer you a $79 plan with 1 gigabyte and I suddenly change it to $59, what is your behavior going to be? It's still not clear. So I think what needs to happen is that operators need to have a lot of good data. And that means that they need to have systems in place to measure and monitor the usage of their subscribers and to see the direct impact onto their network, and then therefore update their planning going forward. That's the only way they can really sort of alleviate their problems. And luckily for most operators, they can always learn from someone else, which is what tends to happen a lot. So a very long-winded answer to your very interesting question. So I hope that covers it. Yeah, so that was a really good question, because I think it actually summarizes the whole discussion around packet data and the importance of planning, as I highlighted at the beginning. So what I might do now actually is, there's a lot of statistics and formulae which I really don't want to go through today, and perhaps aren't all that relevant. So they're there for your reference material. What I would like to do is maybe take a very short break for no more than 5 minutes, and we'll get back to the lecture. Does that sound all right?